Hello students, welcome to All Force e-learning. So let us go for a very important concept, that is finding number of waves in a medium. When the light is entering into a medium from vacuum, so whenever it is traveling in the medium which is optically dense, or whenever it travels through certain distance, how many number of waves will be accommodated in it. Then how we can find the number of waves which are accommodated in the medium when it is travelled through certain distance in it. So that is the concept. Okay. So there are two cases. Case number one, for normal incidence, there is a medium of thickness T and refractive index mu, and the light is incident normally. Means case 1 for normal incidence. When the light is incident normally on this glass plate or any medium and whose refractive index is mu. Now, mu is equal to, as we know that condition, mu is equal to C naught by C or lambda naught by lambda. So already we discussed this absolute refractive index of material medium. Okay. Now here, the time taken to travel this light in the medium is, say, lambda naught is the wavelength of the light in the vacuum, that is from air or vacuum into the material medium or optically denser medium whose refractive index is mu. Then whenever it is entered and travels certain distance, that distance is, say, t. Now, how many number of waves will be accommodated or presented in this material medium in traveling through this distance t? Now, the time taken. What is the time taken by this wave to travel through distance t in this material medium? Time is equal to path length. What is the path length? From here to here, thickness is the path length by velocity of the light in the medium. So, path length by velocity. Just time is equal to path length t by velocity c. But velocity v or c equal to n lambda, where n is frequency. Therefore, t by n lambda, where n is frequency taking this side, then time into frequency. Here, the time into frequency which gives number of waves, that equal to t by, so remaining lambda, that lambda equal to lambda naught by mu. From where we are getting here lambda, here it is, lambda is equal to, from this equation, lambda naught by mu. Just this value substituted instead of lambda, and n is taken this side, and time into frequency which gives the number of waves, and here by simplifying mu t by lambda naught. So the number of waves accommodated or presented in this medium in traveling through a distance t in this material medium whose refractive index is mu, that equal to mu t by lambda naught. So here the number of waves equal to mu by lambda, that is constant, then path length. What is the path length here? T is the path length. T is path length. So this is the way to find the number of waves which are accommodated in the medium. And go for the case 2. So we cannot expect all the time the light is incidenting normal to the material medium. Okay? Sometimes it is also incident at certain angle of incidence with the normal. See the case 2. So light is falling at an angle of incidence I on the material medium whose refractive index is mu. Then here the light is refracted and traveling through distance AC. The path covered by the light in the medium is AC. Therefore, AC is the path length. Okay. Now from this triangle ABC, we can take cos R equal to T thickness adjacent side by AC. AC is equal to T by cos R. So what is this AC path length? Why? Because we use the logically directly we can substitute mu by lambda naught into path length. Mu by lambda is constant. Keep it aside. So here the number of waves in the medium is equal to mu by lambda naught, and the path length is AC. AC, instead of AC we substitute T by cos R. So this is the formula to find the number of waves which are accommodated, which are presented in the medium as it travels through certain distance in the medium when angle of incidence is I with the normal. Of course, for normal incidence, directly we can take this mu by lambda naught into path length. So let us go for one suitable example. So that example is, see, a ray of light is traveling in a medium. A ray of light is traveling in a medium. This is example problem. Whose wavelength is given 5000 angstrom units. 5000 angstrom units. This is wavelength of the light traveling in vacuum. Okay. It is inciding on a material medium which is a diamond. So diamond refractive index is 2.417. This is diamond. Okay. Now it is light is incident normally on the diamond, and it travels through a distance. How much? Its thickness is given. Diamond thickness is 1 millimeters. Thickness of the diamond is 1 millimeters. Once again, a ray of light is traveling in a vacuum whose wavelength is 5000 angstrom units, and it is incident on a diamond material whose thickness is 1 millimeters normally. It is incident normally, and the refractive index of the diamond 2.417. Then number of waves accommodated are presented in the diamond as the light is traveling through 1 millimeter in the diamond. Formula is for normal incidence. Formula number of waves is equal to mu by lambda naught into path length. Yes, mu is 2.417 by lambda naught 5000 angstrom units, convert into meters minus 10. Okay. Now you will get this substituting 1 millimeter and 10 power minus 3 convert into meters. Then simplifying this, 48 roughly it is 4838 waves will be presented in it. So this is your answer. Okay. So for this question, what are the number of waves which are presented in the diamond of thickness? Diamond of thickness of 1 millimeter when light is traveling in the diamond whose wavelength in the vacuum is 5000 angstrom units. 5000 angstrom units. Okay. Let us go for another concept. Next point is critical angle and total internal reflection. Your next concept is critical angle and total internal reflection. This is shortly we call it as TIR. Simply it is TIR. So very important concepts. One is critical angle, other one is total internal reflection. Critical angle generally represented by C. Okay. Now, as we know, regarding the refraction of light. When the light is traveling from rarer into denser medium, it bends towards normal. When the light is traveling from denser into rarer medium, it bends away from the normal. Yeah, let us consider the glass slab. Now object is under this glass slab. See, this is object. Its refractive index is mu. So this is air medium, which is started from the glass and entering into air because object is here. Now the light ray is traveling from glass into air medium, that is denser into rarer. It bends away from the normal. It bends away from the normal. So this is the angle of incidence, this is the angle of reflection. Okay. Now in this case, whenever the angle of incidence increases, the corresponding angle of refraction will also increase. So as this angle of incidence gradually increases, angle of refraction will also be increased. Right? So in the second case, suppose let us increase the angle of incidence, that by incidenting one more light at somewhere at greater distance. Now here a normal is drawn. Normal is drawn. Now here angle of incidence I is greater than this one. Now whenever the angle of incidence increases, angle of refraction will also increase, and it grazing the surface separating two media. Now it is grazing. Now angle of refraction that becomes 90 degree in this case. Okay. Now case 3, suppose this angle of incidence is said to be critical angle. Here I is equal to. So at critical condition, when the light is grazing the surface separating two media, at critical case I is equal to, say, critical angle, R is equal to 90 degree. Okay. Now one more point here, when ray of light is incident some other point where the normal is drawn. So here angle of incidence definitely greater than the C value, and critical angle, it is greater than critical angle. What happens? Instead of getting grazing or refraction, it undergoes reflection into the same medium. Means the light is started from denser medium, incident at the boundary. When angle of incidence greater than the critical angle, then instead of entering into another medium, the light will reflect into the same medium, that denser medium. So this phenomena is known as total internal reflection. Means reflection takes place into the same medium, that is into the denser medium, when angle of incidence is greater than the critical angle. So these three situations we can understand properly. That first case is already we discussed a lot regarding the refraction of light as the light traveling from denser into rarer. The second case is a new one, that is giving the critical angle concept, when angle of incidence in the denser medium, for which angle of refraction in rarer medium becomes 90 degree. That angle of incidence is known as critical angle. Once again I repeat, when a ray of light traveling from denser into rarer medium, the angle of incidence in the denser medium for which the angle of refraction in the rarer medium becomes 90 degree, and such angle of incidence is known as a critical angle. Such angle of incidence is known as critical angle. Therefore, for a critical case or concept or discussion regarding the critical angle, therefore we take the condition I is equal to C, R equal to 90. Its refractive index mu and air refractive index is 1. Therefore, mu from Snell's law, right? Mu into sin I is equal to mu air into sin R. Okay? Mu sin I is sin C. I is equal to C. That equal to mu air 1. So sin R sin 90. And you will get sin C is equal to 1 by mu. From this, you can find the critical angle. C is equal to sin inverse 1 by mu. This is the critical angle. So for a critical angle, light is grazing the surface separating two media. For the critical angle, light is grazing the boundary which is separating two media. Of course, here at angle of incidence which is equal to critical angle, instead of entering into the radar medium, the light just grazing the surface separating the two media, which is known as critical angle, and its critical angle is equal to sin inverse of 1 by mu. Okay, so this is regarding critical angle. So already mentioned that when angle of incidence is greater than the critical angle, then which leads to totally refracting the light into the same medium, which is known as total internal reflection. What is the significance of total internal reflection? The total internal reflection in the sense totally reflect. Totally reflect means there is no loss of energy in this reflection. So even a negligible percentage of light is not lost during this reflection. Therefore, the light, whatever the light is started from here, that incident on the boundary, so total light will be reflected without any loss is known as total internal reflection. Why it is internal? So the light is started from denser, that will be reflected into the same medium, therefore internally reflecting, but totally reflecting, which is known as total internal reflection when angle of incidence is greater than the critical angle. So this is a matter regarding this critical angle and total internal reflection. I will discuss in detail regarding the total internal reflection and the critical angle. So let us go for significance of critical angle. So critical angle is very important note point. Note. Critical angle is not concerned to the single medium alone. What does it mean? The critical angle is not concerned to the glass plate alone if you consider the denser medium glass plate. So glass plate itself is not deciding the critical angle. Keep in our mind, the critical angle is decided by pair of media, that the glass plate and which is keeping in another medium. From glass into another medium the light is traveling, and the pair of the media through which the light is traveling is deciding the critical angle. Means the critical angle is not concerned to single medium alone, that is the denser medium alone. The critical angle depends on pair of the media through which light refracts. Means in this case the glass and air together will decide the critical angle. So without the considering the air medium into account, the glass never decides its own critical angle, so it is wrong. It is pair of the media. Suppose if you go for the glass is keeping in water medium, so water and the glass together will decide the critical angle. The glass itself only not giving the critical angle. So once again I repeat the same statement, the critical angle is not concerned to the single medium alone, which is the denser medium alone. The critical angle depends on the pair of the media through which light is refracting, through which light is passing. So this is very, very important. Therefore, based on this statement, I would like to give one example. Example problem, go for example. Suppose the light is traveling from glass into air medium. Light is traveling from glass into air medium. Then what is the critical angle over here? So finding the critical angle when the light is traveling from glass into air medium, formula is sin C is equal to 1 by mu. Glass with respect to air or glass with respect to vacuum. So glass directly we can write it as sin C is equal to 1 by 3 by 2, which gives sin C is equal to 2 by 3. C is equal to sin inverse 2 by 3, which gives us 42 degree nearly. This is the critical angle for a glass when the light is traveling from glass into air medium, where the light is grazing the surface separating two media. Its corresponding critical angle is 42 degree. Yes, let us go for one more example, that finding the critical angle of pair of media as the light is traveling from glass into water. See, consider here it is a glass which is keeping in water medium. Okay. Now, glass refractive index is given 3 by 2. Water refractive index is 4 by 3. Light is traveling from glass into water and it is grazing the surface separating glass and water. This is the critical angle C dash, suppose. Now in this case, sin C dash is equal to 1 by mu glass with respect to water. Here mu glass with respect to vacuum or with respect to air medium. Air and vacuum refractive index taken to be 1, so that here directly we are substituting 3 by 2. But here it is not so. It is sin C dash equal to, so here 1 by mu glass by mu water, reciprocal mu water by mu glass. Then sin C dash equal to how much? 4 by 3 by 3 by 2, which gives us 8 by 9. Therefore, sin C dash is equal to 8 by 9. 8 by 9. Then what is its value? Let us see. 8 by 9 in the sense, see here. Sin C dash or C dash equal to sin inverse 8 by 9, which gives us nearly 62 degree. 62 degree. Now here the glass from which the light is started. So in the first case, first example, the light entering into air medium. Here the critical angle 42 degree. Here also light started from glass entering into water medium. But here the critical angle is changed. It is not 42 degree, it is 62 degree. So that's why the critical angle is not depends on the glass medium alone or denser medium alone. It is the pair of the media. It is proved by these two examples. In the first case, 42 degree critical angle. In the second case, as the light is traveling from glass into water, critical angle is 62 degree. As the light is traveling from glass into air medium, critical angle 42 degree. Therefore, here the critical angle will decide. Critical angle is inversely proportional to mu, relative refractive index. Mu glass with air or vacuum, or C is inversely proportional to mu glass with respect to water. As we know that glass with respect to water, relative refractive index here with respect to vacuum it is absolute refractive index. Absolute refractive index generally greater than 1. Its value is more than that of relative refractive index. If mu is greater, C is smaller. Mu is smaller, C is greater. So therefore here mu and C are inversely proportional. So for relative refractive index, glass with respect to water is decreases, thereby the critical angle increases in this case. Okay, so this is how to understand the critical angle, what is happening, how it depends on the pair of media, so everything is over. And one more point here, the critical angle and total internal reflection. Total internal reflection. Let us go for the discussion over the total internal reflection. Okay? So let us try to understand the critical angle and which is leading into total internal reflection. And from ordinary refraction, see here, from refraction into critical to TIR. So how we can understand this by this teaching aid? So I try my level best to make understand properly. See here, this is incident light, this is incident ray, this is the refracted ray. Okay, see clearly. So this is incident ray, this is a refracted ray. So normal is done at this point of incidence I. Suppose if I increase this angle of incidence slowly, see what happens there. Observe that clearly, R value. As it is increasing slowly, angle of incidence, see here, angle of incidence increases, angle of refraction also increased. Like that, if you are going to certain amount, then what happens here? Clearly, see. So this light is grazing the surface separating two media. Here R becomes 90. This angle of incidence is known as critical angle. Suppose further, if angle of incidence increases further, then what happens here? See. So if further increases, see. So again it reflects into the same medium. So it started from denser, entering into denser. This is the TIR case. See here, this is the ordinary refraction. And for the critical angle, we are increasing the angle of incidence such that the refracted ray grazing the surface 90 degree R. This is second case, critical angle. And further angle of incidence increases. So it becomes totally reflected into the same medium. This is total internal reflection. Okay. Now this is the way to understand what exactly happening there. Now, so here for total internal reflection, what will be the condition? In order to get the critical angle and in order to find the result that in total internal reflection. So there are some conditions. Before going to those conditions and total internal reflection, let us go for the critical angle. So factors affecting the critical angle, let us see that. After that, after completion of that, we go for total internal reflection. Okay. Now, here factors affecting the critical angle. Okay, right. As we know that the critical angle sin C is equal to 1 by mu. This is a condition. Okay, for critical angle. See here, this is a glass plate. Of course, any denser medium, its refractive index mu. So light is incident on it, and it is grazing the surface separating two media. This is medium 1, say it is medium 2. It is denser medium, it is rarer medium. Okay, denser into rarer, and here the light is grazing the boundary which separating two media 1 and 2. Here it is critical angle, this is 90 degree. From this you are getting this condition. Okay, therefore in this case sin C is equal to 1 by mu. So mu is equal to, or mu C is equal to, C increases. As C increases, sin C will also be increased. Therefore we can take directly C is inversely proportional to mu. Okay, here just now we discussed mu increases, C decreases, mu decreases, C increases. Therefore, factors affecting the critical angle, point number 1. Point number 1, whenever the critical angle is, that critical angle is inversely proportional to density of the material medium. How it is inversely proportional to density? Means material density will also be influence the critical angle. How it influence? Here, mu is directly proportional to D. Means density is greater than, suppose density is greater, which is optically denser, definitely refractive index is also greater. So we can understand that by the air medium or vacuum, one, no medium is there. The next air medium, so density somewhat increases. Next water increases. Glass, diamond, like that the density increases, refractive index is also increased. Therefore, these two are proportional. As such, C is inversely proportional to mu. As mu is directly proportional to D, therefore critical angle is inversely proportional to density of material medium. Okay, this is density changes, density of material changes, critical angle changes. If density more, critical angle is less. Next point. So critical angle is directly proportional to the temperature. It is directly proportional to temperature. As temperature increases, what happens? As the temperature increases, density decreases. When density decreases, that is directly proportional to, so that is 1 by mu. Simply here, we can take directly between the temperature and refractive index. Here, 1 by mu is directly proportional to T. Here, 1 by mu instead of 1 by mu, we can directly straight away substitute the temperature here, directly proportional to temperature. Means as temperature increases, the material medium becomes less dense. If density less, critical angle is more. Therefore, temperature is more, critical angle also will be more. Then next go for third case. So critical angle is directly proportional to wavelength of the light used. So in this case, so as we know that by the third case, since here refractive index is inversely proportional to wavelength, inversely proportional to wavelength. As this relation is giving that inversely proportional, lambda is inversely proportional to mu. Okay, here C is directly proportional to 1 by mu. So 1 by mu instead of this value, straight away we subtract lambda value, then critical angle directly proportional to lambda. Means when we use glass air medium in which red color light is used, for red color light wavelength is more, therefore for red color critical angle is more, and like that in accordance with wavelength critical angle changes. So from red to violet critical angle decreases. So these are the three factors which influence the critical angle. Okay. Now next point is, let us go for total internal reflection. Okay. As we know that total internal reflection, what does it mean? So that total internal reflection in the sense, the total light will be reflected into the same medium. Which medium? Denser medium. Okay, right. So total internal reflection will take place whenever the light traveling from denser into rarer medium. Otherwise, you won't get total internal reflection when the light is traveling from rarer into denser. Rarer into denser. It is not possible at all. See here, let us go for teaching aid using to understand this, what exactly happening really from denser into rarer, how it is giving TIR, from rarer into denser, why don't it give the TIR? Let us see by using this teaching aid. Okay, right, here in this case light is traveling from one medium into another medium, so it undergoes refraction. That I and R, it is ordinary. As angle of incidence earlier given this C. So this is a denser medium, this is rarer medium. As angle of incidence increases slowly, what happens here? Angle of incidence increases and angle of refraction will also increase at a particular angle of incidence, then it is totally reflects into the same medium. This is total internal reflection happening whenever the light is traveling from denser into rarer medium. If you are taking reverse, suppose light is coming from rarer into denser medium, it bends towards normal. This is R, this is I. Let us verify by using this teaching aid. Okay, now this is incident light, this is refracted. Suppose angle of incidence increases slowly, then what happens here? Angle of refraction will also be increased. See here, angle of incidence, so this is angle of incidence is I, this is R. As this angle of incidence increases, angle of refraction will also increase. So whenever it is becomes 90 degree, which one? Angle of incidence. Still it is in the second medium. So we cannot move inside the denser medium. Light will not be move, that is traveling from air, that is rarer into denser. So we cannot go inside this denser medium, glass medium. It is not possible. Therefore, even if angle of incidence becomes 90 degree, still the light is in the denser medium. Therefore, there is no scope at all to get the total internal reflection phenomena when the light is traveling from rarer into denser medium. Keep in your mind, it's very, very important. So, the conditions for TIR, total internal reflection. What are the conditions? Conditions for TIR. Conditions for TIR. Condition number 1. The light must travel from denser into rarer, or light must pass from denser into rarer medium. Otherwise, you won't get TIR, total internal reflection. Okay? So this is incident light and this is reflected light. This is denser medium, this is R. Okay? Now, second case, second point, condition. The angle of incidence must be greater than the critical angle. See here, if angle of incidence greater than the critical angle, then only TIR takes place. So, what are the basic conditions for TIR? Condition number 1, light must travel from denser into rarer. Otherwise, you won't get TIR. Just now I shown. Second condition. Here, the angle of incidence that must be greater than the critical angle. Then only it undergoes total internal reflection. Okay? So these two are the conditions. And again we go for another differences, two differences between TIR and ordinary reflection. Let us see. So this is total internal reflection takes place, and we discussed earlier that is general reflection. So reflection and total internal reflection, what makes the big difference? Let us see. Differences. Difference number 1. First of all, let us make a discussion over the total internal reflection, what is happening there. So light is, suppose it is carrying some amount of energy, suppose 100 units of energy, where incident energy. That incident energy is incident at the boundary where it undergoes TIR. So again 100 units of energy will be reflected. There is no loss of energy in this case. In total internal reflection, there is no loss of energy. Even if it is making a number of reflections in such a way that under TIR, then even the final light again having the same amount of energy without any loss. So this is the main characteristics, this is the main use of total internal reflection. Whereas ordinary reflection in which what happens? Light incident, a part will be reflected. Suppose 100 units of light is incident. So here some amount of energy undergoes refraction. Say it is of 30 units and 70 units will be reflected. 70 units will be reflected. See here, in ordinary reflection, 100 units of energy will not be reflected. A part of it only reflected, that is only 70 units or something less than that of incident energy. So 100 units, say example, 100 units, 70 is reflecting, but 30 will be absorbed, that is refracts and absorption, everything will be gone through this material medium. Okay, so in this case, total energy will not come out by the reflection in ordinary case, but total internal reflection, it is not so. Whatever the energy you given, the total amount of energy will be reflected. This is difference 1 and difference 2. So in ordinary reflection and total internal reflection, in both the cases, law of reflection holds good. We can apply law of reflection for ordinary one and total internal reflection. For both the cases, I is equal to R. Here also I is equal to R. No difference at all. So law of reflection, that is I is equal to R, angle of incidence and angle of reflection, these two are equal in total internal reflection phenomena and also in ordinary reflection phenomena. Okay, right. Difference 3. Third difference. In total internal reflection, the light must pass from denser into rarer. Suppose light is traveling from rarer into denser, you would get total internal reflection phenomena. Whereas ordinary reflection, which can happen whether it is traveling from rarer into denser, denser into rarer. Even sometimes denser into rarer, the light is traveling. So a part will be reflect and other will refract. This kind of problem we solved at the beginning. So this is a part is refracted. So in this case it is 100 units, 30 units refracted, remaining 70 units comes out. So this is happening whether the light is traveling from denser into rarer and rarer into denser, in both the cases in ordinary reflection. So this can be possible, but whereas total internal reflection, this is only possible whenever the light is traveling from denser into rarer medium. So don't think of that, sir. Here in this case, light is traveling from denser into rarer. Why don't it get total internal reflection? So total internal reflection will also happen over here, but under a particular circumstances, that is angle of incidence is equal to, greater than the critical angle. Angle of incidence is greater than the critical angle, then only TIR takes place. But till then, so it is giving ordinary reflection. Okay, before reaching that one, it is giving ordinary reflection. So once it reaches, then it is giving TIR, that is different issue. So these are the basic differences, and total internal reflection is happened, right? Everything is given, but once again I am going to give definitions that what is critical angle. So whenever the ray is traveling from denser into rarer medium, the angle of incidence in the denser medium, for which angle of refraction in the rarer medium becomes 90 degree, that angle of incidence is known as critical angle. Okay, what is total internal reflection? Whenever the angle of incidence is more than the critical angle in the denser medium, such that the light will be reflection to the same medium. So this kind of phenomena is known as total internal reflection, and the conditions for TIR are given two conditions, and the differences between ordinary reflection and total internal reflection given, all are over. Then let us move for applications of total internal reflection. So there are some applications for total internal reflection. what are the applications related to it.